Welcome back to the channel. Today we're going to continue with the petroleum battery project in order to reanimate this dead electric golf cart and get it back on the road. If you're new to the channel, well, the petroleum battery is an idea that we've been developing and testing. Basically, the idea is to pitch the heavy and expensive lead-acid batteries and replace them with a small gasoline engine and an alternator from a car. Now, despite the fact that this method is inefficient, we've had outstanding results so far. Anyway, in the previous episode, we were able to fit our new power source into the battery compartment of this electric golf cart. So far, so good. Technically, all we need to do now is connect this drive-by-wire accelerator pedal and this mini power supply, and this golf cart is back on the road. But as luck would have it, today there are no roads that we can drive on. So, yeah, it ain't a lot of snow, but for Kansas, this is enough snow to shut the state down. Meh, that sucks, but it'll give us a chance to focus on some cool features I want to add to this one-of-a-kind project. Well, since we have the time, let's build an automatic choke for the carburetor. And since this engine basically has two speeds, idle and full throttle, let's build an automatic throttle. Now, here's something to keep in mind. This entire project is based on math, and we're not going to get into the math today. But in order to get the best performance and efficiency from this simple petroleum battery, this alternator wants to spin pretty fast. You see, the faster it spins, the less heat it'll generate. So with that in mind, we want the engine to run at 3600 RPM whenever the petroleum battery is generating power for the electric drive motor in the golf cart. You know, it doesn't matter if the golf cart is being driven fast or slow, we always want the gasoline engine to be turning at 3600 RPM. However, when the golf cart is stopped, it would be nice to have the engine idle down automatically. Now, we're still focused on keeping this system simple, so the automatic choke and the automatic throttle are not necessary. These features don't change the basic control circuit, so if you're interested in building something similar and you're not interested in these automatic features, well, just use a manual choke and a manual throttle control. Oh, and while we have the extra time, we're also going to fit a complete and quiet exhaust to this rig. I think a quiet exhaust system on this petroleum battery is going to be a really cool feature. Alright, let's get started. So in the previous episode, we installed this modified Honda GX390 remote choke linkage on this 212cc engine. At this point, we can connect the linkage to a standard choke cable, but we ain't going to be doing that. Instead, we're going to connect this linkage to a $20 electromechanical gizmo. Of course, due to the snow and ice, well, it took a while for this gizmo to arrive, and it's here. You know, for $20, this appears to be a great value if we can get it to work the way we want it to. So this thing is a cable pull servo. Well, not exactly a true servo because it doesn't have a feedback device built in. Instead, it has two limit switches inside the housing. So when this thing is activated by applying 12 volts to the trigger wire, it'll pull the cable in. Once the 12 volts is removed from the trigger wire, well, it'll release the cable. This is exactly what we need for our automatic choke. Let's power it up and see how it works. So the red wire is connected to 12 volts, the yellow wire is connected to ground, and this green wire is the trigger signal. Eventually, we'll connect the green wire to the starter switch, and when we crank the engine over, that'll trigger the servo to pull in the choke linkage. Well, that's the plan. And action! Not too shabby. You know, it's a bit noisy, but it works. Let's pull the cable in, and then I'll mark it with a Sharpie, and then we can release the cable and find out how much travel it has. Alright, let's measure that travel. And it looks like we have about 46 millimeters of travel, and that translates to 1.8 inches. I think that's way too much travel, and we only need about 20 millimeters or 3/4 of an inch. Well, let's open this thing up and see if it can be modified easily. It would be nice to be able to reduce the amount of travel this thing has. Okay, so this is interesting. It looks like we have a lot going on the front end of this thing. We have an electric motor with some gears and some kind of a screw drive. When the motor is energized, it spins the screw and it pulls the cable in. That makes sense. Now this thingy's connected to the screw drive and it'll move with the cable. The purpose of this thingy is to activate the forward and reverse limit switches. So it kind of works like this. Now on the circuit board, we have 2 relays, 2 limit switches, a diode, and possibly some sort of device to limit the inrush current. Well, the bad news is it looks like nothing is adjustable. Now it does look like it may be possible to 3D print something that'll fit inside this slot, and that would extend the reach of this metal thingy, and in turn that would activate the limit switches sooner. I think that actually would work, but I want to try something different first. You know, perhaps we could add a spring-loaded extension to the front of this thing, and any excess travel would be absorbed by the spring. So I do have the raw material in stock to make something on the lathe. Just for fun, let's try to build something. Basically, we would drill out the inside of this bigger chunk of aluminum, and that'll allow this smaller chunk to slide inside, and then we can use a spring to absorb the excess travel. This will definitely make a lot more sense in a moment, but first we have to build the parts. The threads we have to cut are 10mm with a 1.0 pitch. I think that's how you say it in metric. You know, I actually do all my measurements and designs and machine stuff in metric, but most of the time I use imperial nuts and bolts to assemble the parts. I'm sure that would give the metric crowd nightmares. Meh, imperial nuts and bolts are cheap and easy to get here in the States, and I'm very comfortable working on stuff with both metric and SAE fasteners. You know, it's actually common to find a mixture of both metric and SAE fasteners on American-made stuff, especially on lawn and garden equipment. Alright, now we have all the parts for this semi-convoluted system to limit the travel of the servo. The larger piece screws onto the servo, and the smaller piece fits inside the larger part like so, and we'll use this spring to absorb the excess travel. Theoretically, this should work. The cable that's used on this servo is thicker than a standard bicycle cable, so we'll have to use a cable casing for a motorcycle. I believe this casing is actually for the front brake on a moped. It's hard to say, but it was in my stash of stuff and it fits the cable perfectly. Let's hook this gizmo up to the choke on the engine and see if it works. So the idea is, we'll use the signal from the ignition key when the electric starter is engaged. In theory, as soon as the engine starts cranking over, well, it'll pull this choke in and the engine will start. For this test, we'll just jump the trigger wire. And action! It works! So it's a bit slower than I expected, and I'm okay with that. But we're going to be basically using the same system for the throttle, and that's going to be a problem. On our prototype, we had an adjustable throttle for the engine, and we could continue using the simple throttle. However, on this build, we're going to get rid of the hand throttle and automatically control the engine throttle with one of these servo gizmos. You see, the way the petroleum battery works is, the engine has 2 speeds. It has idle and 3600 RPM. Remember, the drive-by-wire foot throttle actually throttles the alternator and not the engine. So basically, when we press down on the accelerator, we want the engine to go from idle to 3600 RPM. That way, the engine can develop maximum horsepower and the alternator can generate all the voltage it needs to. Now, if you watched the previous videos, you may remember that when the drive-by-wire accelerator is pressed, we have a slight delay before the golf cart starts moving. Well, this annoying delay is now a feature, and it's going to provide us just enough time to get the engine to go from idle to 3600 RPM. So if it's not already clear, the system will have 2 throttles, one for the engine and one for the alternator. The engine throttle commands the engine to go from idle to 3600 RPM, and the alternator throttle, well, that works exactly how you would expect a regular foot throttle to work and provides the driver with variable speed control. Now, keep in mind, the automatic engine throttle control is not necessary and it's more of a luxury, and a hand-controlled manual throttle will get the job done. Now, I'm okay with the slow reaction of the choke servo, however, I feel like that's going to be a problem with the automatic engine throttle. So this time around, we're going to 3D print a spacer that'll fit inside the servo, and that'll reduce the amount of travel the servo has, and in effect, that'll speed up the response time of the engine throttle servo. This time of the year, the shop is obviously a bit colder than normal, and unfortunately that causes the 3D printer to display an error message. So I cheat a little bit and use this hairdryer to warm up the printer enclosure in order to make the error message disappear. It works. Now the part I'm printing is made from ASA plastic, which has properties that are similar to ABS plastic, so what that means is this part can tolerate the heat it may be exposed to, and no worries. And we have a 3D printed solution. Let's see if it'll work. This is the servo we plan on using for the throttle, and as you can see, I've already fitted it with a travel limiting spring gizmo. It works, but it's really slow. Off camera, we've already tested it, and it takes about 3 seconds to go from the idle position to the full throttle position, and that ain't gonna work. I'm hoping the 3D printed part will help speed things up, and we can get rid of the spring absorbing travel limiter doohickey thingy. Okay, we're in. There's actually not a lot of space inside this thing for the 3D printed part. I think this servo gizmo would definitely have a lot more applications if they made it adjustable, but I think this simple hack will do the trick. Anyway, the 3D printed part fits like this. Not too shabby. The metal piece fits into the printed part like this. You know, I'm not sure what I would do without a 3D printer. It saved my bacon so many times. So, full disclosure, I had to print a number of these things before I got something that would actually work. These parts were designed with Tinkercad. Now, Tinkercad is a free resource for idiots like me who don't know how to use a real CAD program. Anyway, let's put this servo back together and we can work on our next challenge. So in order to get the petroleum battery to work, we're going to need to replace this factory accelerator pedal with a drive-by-wire accelerator pedal from a video game. As you can see in this diagram, this pedal is connected to a PWM power supply that we're using to throttle the alternator for the simple version 1.0 that we're building. Now, normally this ain't a big deal. However, we also need to put a trigger switch on this game pedal to activate the servo for the engine throttle. And that's a problem because there's no place to put a switch on this pedal. Now, I've looked at this pedal for a long time and I just couldn't come up with a way to attach this switch. So we're going to have to build some more stuff. So the new plan is to leave the original accelerator pedal in place and build some sort of linkage that attaches to this rod. This linkage will connect to the drive-by-wire pedal, and it'll also allow us to build some sort of way to trigger the engine servo throttle switch. There are probably a million different ways to do this, and I went with a method that allowed me to use parts I already had in stock. So the first thing I needed to do was remove the throttle thingy from the pedal assembly, and I could build something around this guy that would connect it to the linkage that's already in the golf cart. And here we have a bunch of parts to do just that. This is a belt crank that interfaces with the linkage in the golf cart. It's actually just a chunk of steel with a 5/16 bolt welded to it. This is a bracket that bolts to the frame of the golf cart, and this is a piece of aluminum that holds everything together. This is a modified split collar that I'm going to use to hold some bearings in place, and this is another chunk of steel. And finally, these are the bearings we'll be using. You know, I honestly don't remember how all this stuff goes together. You see, I took this stuff apart about a week ago so I could paint the parts, and it's a little bit fuzzy. So I'm going to go ahead and fast forward this part because it does take me a while to assemble this thingy. Now, from my notes, I know this bearing needs to be offset about 4 mm in this split collar for everything to line up. And the good news is I did take one note. Now these metal thingies need to be perfectly aligned, and to do this I'll put it in a vise, and then I can tighten this nut and I'll be right back. Alright, that didn't take long, and now I can continue assembling this thingy. So the way I fabricate stuff is called freestyle, and I just make things without doing any drawings or any measurements. This gizmo is a perfect example of the way I problem solve. I have a vague idea of what I need and I just build something that'll work. You know, a lot of fabricators do this and it's not anything special. The only bad thing about freestyle fabrication is, well, there's no documentation if I wanted to build a second part. And there we go. This will connect the accelerator pedal that's already in the golf cart to the drive-by-wire throttle thingy. Like I mentioned earlier, there's probably a million different ways this can be done. I just did it using material I already had in stock. Now these two holes here is where we can install the trigger switch for the throttle servo gizmo. And fast forward, the limit switch is in. Now if I move the bell crank a little bit, that'll activate the trigger switch and send a command to the servo to pull on the engine throttle. And since we have a slight delay before the alternator starts producing power, well, that should give the servo just enough time to get the engine up to 3600 RPM. So this throttle thingy doohickey whatchamacallit attaches to the frame of the golf cart. Now this hole is a factory original hole, and I had to drill this other hole. Anyway, this thing drops right in, and the accelerator pedal linkage attaches like this. Fast forward a few minutes, and now we can do a quick test. The trigger switch is obviously working, which is really nice, and I'm really happy with that. And it looks like we're getting almost 97% of full movement of the drive-by-wire throttle thingy. You know, it ain't 100%, but that's okay. We can compensate for that in the calibration, so it's not an issue at all. So we're going to go ahead and test all this stuff in a moment, but first let's take a look at the new exhaust system. This exhaust was actually really easy to build. Now if you recall in a previous video, I spotted this mini bike exhaust on the jungle site and it looked like it would fit. And nope, it wasn't even close. I did end up cutting this part off and just built the rest of the exhaust from standard 1-inch tubing. The reason I put this flange here is so we can swap in the little diesel engine in the future, so that's something to look forward to. Now, some of these welds are really bad, and that's because I'm not a welder, but I do play one on YouTube. Anyway, this flex joint is the smallest I could find, and I used some washers to reduce the input and output holes. Anyway, the muffler is from a Subaru Robin EX21 powered generator, which has a 7 horsepower engine. Now, this muffler is something I had in my stash, and from what I'm told, these mufflers are extremely quiet. Now, I hope that's the case and we don't lose too much power with this muffler. It'll be interesting to see how all these random parts work together. Anyway, let's install the exhaust system and we can get the engine running. Now over on the back side, I have the muffler supported with 2 rubber hangers. Now this muffler is actually pretty heavy, which may help in keeping things quiet. Let's see how much flex is in the system. Wow, I didn't expect the engine to move that much, but if it does, there's plenty of flex. This should help keep the golf cart quiet and of course reduce any vibrations. Once again, not too shabby. Fast forward a few minutes and now we have everything hooked up. Now this is all temporary. Once we confirm this stuff works, I'll mount the servos and build a proper electrical harness. That's actually the easy part. Now over on the ignition switch, we have a temporary jumper for the choke servo. We're actually going to remove this jumper for a moment just to see if the cold engine will start without the choke engaging. Yeah, I know this is kind of pointless, but I want to see the difference the choke servo makes. Alright, let's crank the engine over without a choke. Well, almost, but we definitely need the choke, so let me hook the jumper wire up. So both the choke and the throttle work, and I can tell that the engine's running slightly lean and I may have to fiddle with the carburetor jets. But that's no big deal, I have plenty of jets in stock for these little engines. Now this is unfortunate, but the camera makes this thing sound louder than it actually is. It's actually pleasantly quiet, well, within reason, but it's definitely heaps quieter than the prototype was. Yeah, the noise the prototype made was a bit much. Anyway, this new exhaust made a huge difference, and I'm really looking forward to taking this contraption on its first road test when the snow melts. Let's take another look at the automatic choke and the automatic throttle. Ah, very nice, very nice. Now, the purpose of the petroleum battery experiment is to get rid of the heavy and expensive lead-acid batteries. But we do need to have a tiny battery for the electric starter and to run the PWM power supply. Right now, the little battery seems to have plenty of power to keep everything working for an extended amount of time. You know, during the 10-mile trip we took about a month ago, the little battery had no issues keeping up with the electrical demand, and that's awesome. That's why I made the battery charging issue low priority. Now, obviously it would be nice to have a way to keep the little battery charged. I mean, wouldn't it be awesome to have an electric golf cart that didn't need to be plugged into a charger? Well, we're halfway there. The petroleum battery provides plenty of power for the drive system, and why not tap into it so we can keep the little battery charged? Anyway, no worries, the parts have arrived for the onboard battery charging system, but that's something we'll cover in a future video. I think the next step is to mount the servos and finish the wiring harness so we can get this golf cart moving again. Of course, getting the snow to melt is still our top priority, and we're working on it as I speak. I had fun today, and I hope you did as well. If you want to see how this golf cart project turns out, well, consider subscribing if you haven't done so already. You know, at the very least, click on the like button. Come on! And if you want, consider becoming a patron to this channel. I really appreciate all the support from my patrons and my subscribers. It looks like it's going to take a while to melt this snow, so I reckon I'll see you next time. Until then. Alright, so the nut that came with the exhaust pipe from the Jungle site, well, it's not 13mm nor is it a 1/2 inch. The nut is way too big for those wrenches. You know, a 14mm wrench will fit, but it's way too loose. And of course the same thing with a 9/16 wrench. So it ain't metric and it ain't SAE or BSW. I reckon it's something new. Finally, both the metric crowd and the imperial crowd can agree on not liking whatever this thing is.